Alright, so in this tutorial, I'm going to be going through the Runge Kutta fourth order solver, plus some organization stuff. So the organization stuff is just how I like to manage large projects. This is probably not the best way, but this is a way that I found, and some people have told me that it helps them, some people have told me that it doesn't help them. So let's jump right into it. So what is the Runge Kutta fourth order solver? Well, for solving ordinary differential equations, the Runge Kutta method is a solver which does exactly that. It is a numerical solver in that it takes the current value of the function at a current it takes the value of the function at a certain time and performs a computation to determine the next step. And the fourth order solver is the most commonly used. If you're familiar with MATLAB and you've heard of ODE45, that is a fourth order solver with a fifth order correction term, you could say. You can find more info on that in the other video I made, but in here we're going to implement it ourselves because we just want to see how it works and understand where it comes from. As you can see, this is the actual formula for the solver. Basically, to compute the next step, you take the current step and add this value to it. And this value is determined from, is something you'd learn in a numerical analysis course on, where these values actually come from. But we're not interested in that right now. We are simply going to look at implementation. You can find this in any text if you are interested, and I believe the derivation is actually down here. Yes, the derivation is right here if you're interested. But we're not actually interested in the derivation. We're interested in using it, and so let's do just that. The first thing I'd like to okay, and here's where the organization stuff comes in. So the way I like to organize my projects is by having a lib folder, which contains all the libraries of functions that I'll be using. For this project, we have math functions, physics functions, and plotting functions. Nothing too crazy, just some normal stuff. An SRC folder. Normally, I would put objects in here, which we'll get into in a later time. I have a test folder, which is where I just prepare myself for before these videos. As you can see, I've already implemented them, and this is the example we'll be using, and I'll be following. It's code that I know works, basically. You don't have to include a test folder, but I like to do it. And then a temp folder just for temporary files. And then finally, we have this run this only. So I like to run only a single file. Some people dislike that. I personally find it easier. I like to have just a single function to run, and everything else just cascades from there. But yeah, this is the way I will be organizing my projects. So let's begin. So first thing I like to do is just have a start and stop, because I like knowing when my function is finished running, and I like to see it in the command window. To implement the actual solver, we will be looking at what is considered the simple harmonic oscillator. And let me just pull up my reference. Okay, so the simple harmonic oscillator is basically the following system, where we have a mass and a spring, and they are connected as such. And then we define the zero value of this spring as right here. This is a 1 degree of freedom second order system. For those of you who have taken a differential equations class, you'll know that the equations of motion are mx double dot equals negative kx, and this simplifies into x double dot equals negative k over mx. And these are the so-called equations of motion, right? Very, very simple stuff. We don't want to go too complicated just yet, but we do need to use reduction of order to make this into a format that MATLAB can solve easily. So we'll say that we'll define this x vector as x1 and x2. And x1 is going to be equal to x, and x2 is going to be equal to x2. And so the derivative of this x vector is going to be the derivative of x, which is x2, and the derivative of x2, which is x double dot, which is negative k over m x1, right? Because x is equal to x1. And so this is the system that we have, and this will be for MATLAB, right? For MATLAB to solve. So let's code that in. I'll move this off to the side, and let's see. This is going to be in our library. This is going to go into physics function, and we're going to create a new script, and we're going to call this SHO, standing for Simple Harmonic Oscillator. And I'm just going to pull up the thing I have. So yeah, so we have our function. We're going to be returning a dx value, right? The change of our state vector. It's going to be equal to the function, which is called SHO. And into it, we're going to feed time, the state, a spring constant, and a value for m, and a mass. Now you might be wondering, why do we have to do time first? Well, it's just to make things easier, right? If we have any time dependence, we want that time dependence to come first. Next up, we have the state vector, which, pretty straightforward. That's the thing that we want to be performing our operations on. And then finally, we have our k and m, right? These are just constants that, we want to define outside of this function, right? We don't want to be defining constants in a function if we don't need to. And so copying straight from, the math we did, we have dx1 and dx2. And dx1 is going to be equal to x2, and dx2 is going to be negative k over m times x1. Oops, there we go. And so this is our equations of motion for a simple harmonic oscillator. Nothing too advanced. Yeah. So the other thing we should do is we should define, how to actually run this thing. And so to do that, let's go into run this only, and let's set up what we care about. So first we have to do a time span, right? There's a time span over which our simulation will run. And then we have our solution, right? And then, maybe we have some constants, right? Things like solution span, I'll call it. And then we have some constants, and then we have our solver, and then we'll have something for plotting, right? Now, something I did not mention here is that while we are in this folder, the KV modeling folder, we can't really access the functions in here. And so to do that, we have to create a new a section here. And it's going to be called I'll just call it folder access. And essentially, all we have to do is tell MATLAB that we want to add some other stuff, some other paths to our path. For those of you who are in comp sci, that was probably a very weird way of saying it, but I'm not a comp sci major, so I have no idea. That makes sense to me. Essentially, what this line does is it adds the path of lib and everything inside of it. So anything that is now in this lib folder, which would be our physics functions, is now available when we run this script, as soon as this line executes. Right now, we only need to do lib because we're not going to be putting anything in the other folders. But this is just something that we should add. Next up, let's define our time span. So our time span is going to be, well, let's start small. Our time step is going to be 1 out of 100. It's going to be 1 divided by 100, and our time span is going to be from 0 at this time step up to 10. Nothing too long, just something that we can see what our solution looks like. And then we have to define our variables. So x naught. So this is the initial state of the vector. We're going to say that it starts at some displacement and no initial velocity. For those of you who took DiffyQs, they should look very familiar. And we'll define an x span, which is going to be zeros, and we want it to be the length of t span. So, and the length of x0. Oops, x0. And so, okay, you might be wondering where this line comes from. So where this line comes from is, this is our state vector. It's going to be one row with 2 columns. The first column represents position. The second column represents velocity. When we have our solution, we're going to be getting both values for the state vector, right? Our state vector is defined as x1 is the position and x2 is the velocity. And we need both of those to solve this function. So we need to have the length of or sorry, the number of rows has to equal the amount of time that we, or the amount of, for every time step, we need a place to put the value. And we need it to be as long as the state vector is. And so that's where this comes from. I missed a parentheses here. But yeah, it's nothing too crazy. And the other thing we need to do is we need to set the first value of this time span. So in the first row, every column, we want to load in x naught. And that's what we have here. And then we just have to define some constants. So let's say we have a spring constant of 2 and a mass of 1, right? Nothing too crazy. Although this could be changing, or this could be some whatever complicated value you want it to be. And now we have to implement the Runge Kutta solver. So the Runge Kutta solver, let me pull it up again. Here it is. So these are the coefficients and the solver scheme, you could say, right? The numerical scheme that we are using. And so we're just going to implement this in directly, right? You can just go to the Wikipedia page, find these things, and copy them in, right? There's nothing special going on here per se. So let's do that. Let's create a new script. We're going to call it RK4. And within this script, let me pull up my reference. There it is. The way the function works is our output is the next state, which is we're gonna call it x, and the input, or actually we'll call it. Okay, I'm not gonna call it x plus 1, but this right here is x plus 1, right? Or xn plus 1 if you want to be specific. But it's annoying to put plus signs inside of here, right? Like this is not very convenient to have. So I'll just leave it as x. We have RK4. And when we look at the function here, what we can see is that, here actually I'll just move this here and put this here. Perfect. So what we can see is that the Runge Kutta solver, it actually takes in as input what we also need to feed it a function. And so the function is the first thing that we should be putting in. We're going to call it dynamics. This is a general term for something that changes. And the first input is going to be the current time, the time step, the x, and then I don't know how to pronounce this. Vargargin is what I say, but it stands for variable arguments input, which means we could put in as many constants here. They'd all be defined inside of this variable. And let's end the function there. So yeah, this is our function, right? We have to feed it some function, dynamics. This would be our f of our function here. We have to feed it the time, right? Because we care about time and the state vector. But we also need to feed it this dt, which they define it differently, but the step size here, this is our dt. They define it as h here, we're defining it as dt. And then we have whatever variables, our dynamics function would use. And so to implement it, we'll just copy this directly. So first let's define all the coefficients. So we have k1 through k4, and let's see, how are they defined? So k1 is defined as our function. First input is t, and second input is x. And because it's our function, we also have to feed it the variable inputs. And this is the way we say that we want to feed it all the inputs. This variable will be I believe it's a cell array, and we just want to make sure that it's feeding in all of those values. So this is the value for the first thing, and we can see that we're going to end up copying this quite a few times. So let's just do that. Now for the second one, we do t plus dt over 2, and the same thing goes in for the next one. So we'll just copy that in, and the last one's going to be t plus dt. This looks a little ugly, so let's just tab over a little bit until it looks cleaner. Yep. So this will take in t, x, and vargin, right? T, the function, and then whatever other variables we need. The second one will take in t plus dt over 2, but instead of taking in just x, it's also going to take in x plus dt times k1 divided by 2. And this comes straight from here. The next one, we'll do something very similar. Plus dt times k2 divided by 2. Sorry if I'm going a bit slow, I just want to make sure I'm not making any typos here. This one will also take in dt, but this time it'll be times k3. And we'll just clean it up one more time so it's a little more organized. And boom, we have our solver. We have all of our coefficients. We don't have the solver just yet. And so the next step is to just get the value of our output, which is going to be this x. So we're going to define it as the output is going to be equal to the input, right, plus our dt times, and I'll move the 1/6 to the very end. So, and inside the parentheses we have k1 plus 2 times k2 plus 2 times k3 plus k4. And just gonna check to make sure I don't have any typos, and this looks right to me. So let's go with it. Yeah, so this is our RK4 solver. I've already said this a few times, but I'm gonna say it one more time. This x is not the input x. It is the x of n plus 1. This is our x of n, right? I want to make that distinction here. You know what? I'll just do that. We're going to call this xn. We're going to call this xn1. Or sorry, no, xn0. And we'll copy paste it over. Just because I don't want anyone to make any. I don't want people to get this wrong. Just because of my naming convention is weird. And I guess for this project, it shouldn't make much of a difference. But yeah, there we go. So we have our previous state, the time step there, and we're getting our next state. And you can see that the time step was just going to increment by a dt value, so we don't have to consider that. We can just do that outside of our loop. And so we have our RK4 solver. Now to actually implement it, I will move this. I'll just minimize this and put this here. So now let's go into getting our solver done. So to get the solver, right? Actually, I'm gonna make a bit more space for myself just by pressing enter a few times. Okay. So to get our solver, what we do is we have to iterate through our whole time step. So for I'll use a as my dummy variable, and we want to go to the length of the time span minus 1. And the reason why is because our RK4 solver computes xn plus 1, which means if we have 100 steps, we only need to go up to the 99th step. The 100th step will be computed by the 99th step, right? So let's just do that. And now that that's done, let's just implement the solver. So x span, we're looking at the a plus 1th row, and every column in it is going to be equal to our RK4 solver, and we're going to feed it our dynamics, which is our at SHO, right? We're calling the function simple harmonic oscillator, wherever that is. Whoops, I'm going to move out to this folder. And our inputs to this are going to be the current time span, so time span A, right? Because actually here, this is a good practice actually. Take your function, copy it, and put it in here, right? Don't make dumb errors. I'll even tab over so you can see that it's exactly there. There we go. We have our dynamics, which is SHO. We have to put in the current time value, which is time span A. We have to put in the time step, which is dt. We have to put in the current state. So if we're trying to compute x span A plus 1, we have to put in x span A and all the columns. And then we have to feed in the variable arguments in. And the variable arguments in this case, would be k and m. So we're just going to copy this, paste it in directly. Boom. And just like that, we have our solver set up. And it matches this format. If your functions are too complicated, it's good to keep this here as a reference. I personally will leave it here just because, if anyone's trying to recreate this, it helps to see it there. If you decide not to, then it's whatever. It shouldn't make much of a difference. There we go. So this should solve our thing. Now we care about plotting. So this isn't too big, so we'll plot two figures. First, we're gonna plot the time span versus x span, and we're only interested in the position. So the position is located in every row, but only the first column, right? That's how we've defined this. We've defined that the rows are going to be the time span, and the length, the rows are going to be all the time steps, and the length, which is the columns, are going to have the different variables of our state vector. And so we want to get every row for every time span, and we only want to get the position, which is the first row, or first column, my bad. And so we'll plot that. Believe it or not, we actually do know what the solution of this looks like, so we'll plot that as well. So figure 2, plot t-span, comma. For those of you who have taken a differential equations class, you'll know that the solution of the equation, as we've defined it, is just going to be, what's it called? Cosine of t-span times, or dot times, square root of k over m. You don't need to know that this is the solution, but it is in fact the solution. So you would learn this in an elementary differential equations class. And the other thing that we're going to plot, which I believe is of interest to us, is we're going to plot the error. So we're going to plot the time span. We're obviously going to plot the original function, right? We want to plot all of this value, all these values, but we're also going to plot the what's it called? The actual analytical solution, which is this right here. So we're going to copy paste this. We're going to put this in. Now, I ran into this problem earlier, so I'm going to just tell you guys right now. When we solve this, it's going to give it to us, but it's going to be transposed. And what that means is we've defined our solution to be, like let's say this is like 10 times 100, so 1,000. This is 1,000 time steps, and it has a length of 2. Unfortunately, this will give it to us the other way. This will give us 2 rows and 1,000 columns. To fix that, we just put the whole thing in parentheses, and we put a single apostrophe. Then this will flip it into the format that we need. And with that, we should be done. So let's run this folder. Run this only, and let's see what it does. Whoops, I made an error. Let's see. Unrecognized variable x1. Oh, okay, yeah. I know where this error is. This should be x0 first. Okay. CLC, just to make it look clean, and run this only. Boom, we're done. So, as you can see, so we have our 3 figures, right? I'll just move them down here so they're easy to see, and I can't scroll down here, so I'll just press enter a few more times. All right, and reopen my 3 plots. So, figure 1 is the plot of the time span, which is this value right here. Second figure is the analytical solution, which we know is the solution. And the third plot is going to be the error. And as you can see, the error is extremely small. This is 5 times 10 to the negative 9. Obviously, it's growing. I believe it's either linear or exponential. We're going to find out in just a second. But you can see that with this error, if this is an acceptable amount of error, our solver is doing a pretty good job of staying with it. Believe it or not, in numerical analysis, you would learn, why this error is the way it is. But yeah, one way we can actually reduce this error, assuming that this wasn't enough, is by further reducing the time step. So keep in mind that we had a step size of 0.01, and we got 10 to the negative 9. But if we were to go in here and make it negative 3, so now it's 0. So we started at 0.01. Now we're at 0.001. And if we run this again, we'll see that our error is now on the order of 10 to the negative 13th, which is ridiculously small, right? The functions virtually look the same at this scale, but there is still the error here. Another thing that we might be interested in is looking at the behavior on a longer time scale. So right now we're only looking at the first 10 seconds. What if we bump that up? What if we look at 100 seconds, right? And so, we run the simulation. Obviously, it'll take roughly 10 times as long. And we can see that, in fact, our error is growing linearly, right? And we can see our solution. It's a little cramped in here, but we can, eyeballing it, we can see that it's pretty much the same thing. They're pretty much the same thing. And so, here we can see the error of our Runge Kutta. It's growing, but it's not exceeding 10 to the negative 10th, right? This is extremely small. Even if we take our step size and put it back to what it was before, we'll see like this error is ridiculously small, right? It's barely going past this value, right? So this was the basics of, doing a numerical solver. This is normally we would be using ODE 45, but the reason why we would choose not to use ODE 45 is if we are certain that, a fourth order solver will keep our errors small, we have no need to use something like ODE 45. We can just get away with using, our own custom solver. Obviously, it's not the best practice, right? In that, if our error did grow beyond a certain amount, right? If our simulation if our simulation was long enough, our error would in fact grow over time. It's just, we're confident that it's not going to, so we will leave it as such. Another interesting thing that we can do is here we're using a fourth order solver. If our if our simulation was a lot simpler, right? If our dynamics were a lot simpler, we could actually even get away with using a lower order solver, which would require, even less computation. So that's just something to think about. Let's see here, see if they mention it here, but yeah. So these are there's other solvers that we could use if we needed to. And yeah. So this has been the first video in the tutorial series. It's how to add in this solver, how to add in some simple equations of motion. This error is fine, by the way. This just says that our variable t is not used. It's a problem that, it's something that we will address further down the line. It's not really an issue, just a warning. And yeah, here we have our solver and the plots that go with it. So if you have any questions, consult a textbook or leave them in the comments, whatever you feel appropriate. And with that, this tutorial is done.